Okay, so yeah, I'm Abhinav and I will be presenting the review of this paper, Fault-tolerant and transactional stateful serverless workflow. This paper has been written by Horan Zhang from University of Pennsylvania, Etni Cardoza from Rutgers University, Peter Bale Chen, Sebastian Angel, and Vincent Liu from University of Pennsylvania. So this paper presents serverless computing and the problems associated with it when you go and try to implement a stateful application, such as a workflow. So what serverless computing is, that serverless computing aims to eliminate the need to manage the machine by the developer. Uh, so the developer does not have to manage the resources and the machine, and it can developer can straight away interact with the API gateway, and the API gateway interacts with the worker. Problem comes when each worker has to persist its state. So for that, the vendors have given one workaround is to persist into the database, either a shared database or isolated database. And if any worker has to interact with another worker, straight away communication with the another worker is not allowed. So this worker has to then interact with the API gateway, and the call will route through the API gateway to another worker. And so if you see here, the problem is that when one is this roundabout way, and another is that each serverless function is expected to be idempotent so that it can be restarted easily. So implementing an idempotent is in itself a challenge. So here the paper comes up with a new framework which promises to take away all the problems of restarting uh, server, serverless functions, logging, concurrent uh, problems due to concurrency, and then application developer can just write the application logic. So the goals, paper defines goals for this framework called BELD. And the goals are here that exactly one semantics, irrespective of crashing, worker should produce results as exactly one without crashing. Then data sovereignty, that is, each worker should have the ability to control its data and expose it to whoever the serverless function wants to expose. Then SSF reusability. So different application can reuse the same SSF at same time. Then workflow transaction. The API should uh, there should be an API to specify workflow that should be processed transactionally with asset semantics and deployable today. Then that is BLD should be the application should be platform independent. That BLD should work on existing serverless platforms without any modification at their end. So BLD is basically uh, based on a previous implementation, that is Olive. So at high level, it is very similar, but the architecture under the hood is different. So below are the components of BLD. So BLD is basically a library which gives API to do operations, take care of logging, and then prunes the logs using garbage collector, and takes care of restarting each stateful serverless function using intent collector. And we'll see that what is how it logs. So here the framework defines these set of tables. So first is the intent table. So intent is basically a set of parameters for a call which uniquely defines a call. So each call has a unique intent ID. So and that intent is persisted into the intent table. And as you see, for read there is a read log, write there is write log, and invoke there is invoke log. So the intent table, as I mentioned earlier. So suppose we take an example of a workflow which has three SSFs. So when a client calls the first SSF, it sends first request ID, and that request ID is persisted by the first SSF into the intent table as an intent ID. And this SSF then generates a unique UUID to call the next SSF and so on. And that unique UUID is used by this SSF2 as its own instance ID. Structure of the logs. So as you see here that intent for intent, the key is instance ID, but for others, the other operation read, write, and invoke, the key is instance ID and step number. And the value for intent ID is done whether the operation is done async, whether it was an async operation or not, what were the arguments sent, the return value, and the timestamp. And for read, in the value, actually the whatever value has been read, suppose price of an item is persisted into the log. For write, boolean is the value, that is whether the operation is complete or not. And for invoke operation, invoke is basically when an SSF calls another SSF, that is invoke. So the value is instance ID of the callee and the result. So paper here tries to co-locate the data and the log so that to avoid any cross-table transactions. And to achieve that is a challenge because each database is different and paper wants to be platform independent. So if you see here, the Cosmos DB, in Cosmos DB, the atomic scope is partition, and data can be like partition can be extended till 20 GB. And in DynamoDB, the atomic scope is a row, a record, and the atomic scope is 400 KB. And in Bigtable, similarly, atomic scope is row, and the maximum size it can extend is 256 MB. So if it wants to record the logs, then it then there has to be something which uh, goes. There has to be some way to link all the records because database has a limited size for row. So the paper comes up with a data structure called distributed atomic affinity logging. So this is basically a linked list of the records, log records, and each record is has a head pointer or a row ID, key, value, lock owner, recent writes, log size, and the pointer to the next log. These were the components of Beldy. Now we will see each of the operations which Beldy allows, that is read, write, invoke, and transaction. So first one is read. So suppose a client gives an operation to execute, that is get item price, which is a read operation. So in that case, what Beldy does, what a SSF will do is first download all the records for that uh, and for that particular operation from the database, create a, a DAL structure in memory, and then traverse that DAL to get the tail to reach the tail. And from the tail, after it has reached the tail, it does the read operation, and then it does the logging. It logs the result to the tail, and both read operation and the logging operation are like combined are not atomic. So it may happen that read is complete and logging fails, which is fine here because even if logging fails and the SSF is again restarted, so in that case, a fresh value can be read again. But in case of write, the logging and the write operation is not is are not independent. They are atomic. They have to happen together. So if you see here, suppose the operation is to write item quantity. So first, what will happen is SSF will check whether the DAL has the log key. So here it will first download the records from the DAL structure in memory, and it will check each node of the DAL that whether it matches the log key. If it is there, then operation has already been executed, that means, and tuple can be found in the current row. So it will return from there. Otherwise, it will go this route that first it will get the tail of the log and try to write in that. And there are three conditions defined for this, that if um, the current log is full, then it will define create a new node and link to it. If current log is not full, tail is not full, then it will write there only. Um, yeah. Then next operation is invocation. So in case of invocation, as I said, that invocation is basically when one SSF calls another SSF. So in that case, first SSF1 calls SSF2, and SSF2 runs the logic. And here if you see, there is a callback to. So this is another instance of SSF1 uh, used to send the callback result. And this instance of SSF1 logs the result here. And then after that, SSF2 marks the operation as complete and logs it in its intent table. So this is done here because suppose SSF2 would have straight away run the logic uh, and marked it has done and sent back the result to SSF1. And if the return would have failed here, then what would have happened that SSF1 would have again uh, re-invoked the SSF2 and the logic would have run again, and the result could be different here. So to avoid that situation, the callback is required here. Transaction. So Belty transaction is based on wait and die deadlock prevention, because the SSF here you do not have much control, so you have to wait actually. So the wait and die is more um, realistic here to use rather than the other one. And two-phase commit is used here. And the protocol has three um, parts. One is creating and forwarding the transaction. So suppose a workflow is within a transaction. So each node, each SSF is passed one uh, transaction context, same transaction context, then executing calls inside a transaction. So there is this begin transaction and end transaction, and within that the call is executed, and propagating abort and commit signal through the workflow. So the if the transaction is aborts, then it has to be transmitted through each node. Similarly for the commit. We'll jump into the evaluation now. So the paper here states that what it tried to achieve by through evaluation and how it evaluated. So it states that basically they try to assess the cost of maintaining the linked DAL and how is the comparison with the application baseline application, that is who do not even implement this uh, uh, this, this paradigm to achieve exactly one semantics actually. And then what is the effect of GC that garbage collector have on a linked DAL traversal, and how much it has effect on the latency of the workflow, and how does it change as we adjust the timeout. So the first one here is build. Yeah. So the first one here is the comparison of Beldy workflow with baseline. So baseline, as I said, does not implement any semantics for exactly uh, that is to implement irrespective of crashing, worker should produce result as exactly as the one without crashing. So that kind of framework is not available with baseline, but still they have implement compared it with that. And if you see the third one is cross stable, that means there is no DAL here. So if you see here, read is latency of read is higher here than the baseline, and it is in fact higher than the cross stable. And for write also, in each of the operation, the latency is higher, and this is because of the usage of the DAL and the logging and the read and write from the database to for getting the data for uh, getting the log records. So these all add to the latency here. That is why if you see BLD has higher latency, and cross-transactional table has higher latency in other applications. Write, conditional write and invoke. So here BLD benefits from having DAL, that is co-location of the logs and the data. The second one here, actually, in the paper, they have implemented a few applications. So this one is movie review service. And here also, if you see, the latency is uh, higher than the baseline. And it reaches a plateau here. And this plateau is because AWS has a limit of 1,000 concurrent lambda per account. As the throughput increases. And then next one is the evaluation for a flight and the hotel reservation system. So similarly, uh, it reaches a plateau here due to the limitation of AWS, and the latency for 50 percentile and 99 percentile is higher than the baseline, because as I said in earlier evaluations, that Weldy does extra work of downloading. The IO is there from for reading from the database and then constructing the DAL and then traversing the DAL and writing into the tail. So those things add up. This evaluation is for a comparison of for the to see the effect of garbage collection. So the if you see here, the cross table transaction has higher latency, the red one, and with collection and without garbage collection. So without garbage collection, it increases slightly after 30, and with garbage collection 1 minute, it is lower, and 10 minutes and 30 minutes are a bit higher than the 1 minute collection. Yeah, thank you.